All right, good morning and welcome to this thermodynamics numerical from NCRT. This is not a straightforward, simple question, although the language of the question is a bit misleading, that it leads you to believe that this is a type of thermodynamic process, but it is not. And I'll tell you the misleading part of this. Okay, the misleading part is that it says the stopcock is suddenly opened. If you see my previous videos, if you know what I have explained, that an adiabatic process, adiabatic process, okay, is always a sudden process, right? Sudden process. So you might start believing by seeing this line that this question is an adiabatic process, and therefore you may feel like applying all the adiabatic equations to this questions, right? Don't do that. Do not do this, and I will tell you why. First, we will read the question, but just a word of caution. Although this looks like a adiabatic process because it's a sudden process, you may be tempted to use adiabatic equations. Do not do that. This is definitely an adiabatic process, but you cannot apply adiabatic equations to it. So let's talk about what type of process is this. It is very weird. I call it adiabatic process, but I ask you not to apply adiabatic equation. First, let's read the question. There are two cylinders. The two cylinders are equal capacity. They're connected to each other via a stopcock. A contains a gas at standard temperature and pressure. The B, which is the second cylinder, is completely evacuated, which means it is vacuum, it has nothing. The entire system is thermally insulated, which means no heat can be exchanged with the environment, cannot be exchanged. If you see an adiabatic process, even an adiabatic process, you cannot exchange heat. Q is 0. Then the stopcock, which is between the two cylinders, is suddenly opened. Then you have to analyze what happens to the final pressure, what happens to the internal energy, what is the change in temperature of the gas, etc., etc. Right? Let's start understanding the situation. Cylinder number one, where the gas is there. Okay, so I will just draw the cylinder number one. It is connected to a cylinder 2, but there is a stopcock, right? This is the cylinder number 2. The cylinder number A, the cylinder number B, right? Equal capacities, the volumes are same volume. They connected through a stopcock, right? In the what happens now? You will remove this. So let me just first show you the gas. Where is the gas? Okay, that is most important. Let's say this is the gas. Okay, this is the gas in the cylinder number A. I hope you're understanding the situation. Okay, now what happens? The stopcock is removed. Okay, I will remove the stopcock. The stopcock is removed. The second cylinder is now in touch with the second cylinder. This is the gas. This cylinder is evacuated. So there is vacuum here. Vacuum. There is nothing here. If you have the gas here, right, and the stopcock is removed, the gas starts moving here, right? The gas starts moving here. The gas starts. So, what is happening to the gas right now? Expansion of the gas is happening. Expansion. The gas is expanding. Expansion. And remember, whatever process you're applying, do not forget to apply the first law of thermodynamics to whatever process you have, whether it's adiabatic, it's isochoric, it's isobaric, or a process like this, which we will shortly discuss. Always remember, you have to apply first law of thermodynamics to thermodynamic processes. Thermodynamics. Do not forget this. This is a larger point, very important. Finally, you will have to apply first law of thermodynamics. Let's come back to situation. This is the first situation. This is the second situation. The second situation, the gas is expanding, right? And this is sudden opening, right? We talked about the suddenness of the process. Then we talked about the system is thermally insulated, right? Which I told you makes you believe it's an adiabatic process. And you may be tempted to apply adiabatic equations, but you are not supposed to. Now let me explain you what happens. This is what is happening. When the gas is expanding here inside a vacuum, the pressure here is zero. There is no pressure here. When the gas moves from a zone of high pressure to no pressure, okay, through the stopcock, since there is no pressure in B, the cylinder B has no pressure. There is no pressure in cylinder B. Therefore, no work is being done. No work is being done. Remember, you must have some pressure on the right hand side. If there is a pressure, the gas which is entering B will have to work to enter that B. But since there is no pressure in B, the gas enters without doing any work. Very important part. No work is done because pressure in B is zero. There is no pressure in B. So no work is being done in this scenario. Such a scenario is called as free expansion. Free expansion. Free expansion. Okay? Free expansion of this type, where there is suddenness, where there is insulation from the external system, the entire system, A and B, both are thermally insulated. No heat can enter A, no heat can enter B, no heat can enter leave A, no heat can leave B. So the system is thermally insulated. A free expansion like this, where the gas is moving from one chamber to another without facing any pressure, is called as a free expansion. A free expansion is also an adiabatic process. Adiabatic process, right? But you cannot apply any adiabatic equation to a free expansion. Do not apply any adiabatic equations to free expansion. I told you. I hope this is clear. There is no pressure and hence no work is being done. The question number one is, what is the final pressure of the gas in A and B? We will come to that. But before we do that, let's understand what's happening from first law of thermodynamics. Second thing you must understand, which is the larger point, okay, the point number two, which you must understand. For this system, what is the net heat entering or leaving? Zero. We just discussed. No heat can enter A or leave A. No heat can enter B or leave B. So the net heat exchanged by this thermally insulated system is zero. What is the work being done by the system or the gas, which is moving from a high pressure zone to evacuated zone through the stopcock? The work done is zero. What is the first law of thermodynamics? Delta U is equal to Q minus W. 0 minus 0 is equal to 0. So the internal energy does not change. There is no change in internal energy. I hope you can understand this. Look at the part B. Look at the part B. No change in internal energy is happening from first law of thermodynamics. I applied the first law of thermodynamics here. The first law of thermodynamics got applied here. Q is equal to 0, W is equal to 0. Therefore, change in internal energy is 0. Right? So this answers your part B. Second, okay, third point, if the internal energy of a system is not changing, right, then what is happening? The temperature cannot change. If you have the internal energy of a system not changing, then the temperature cannot change. Go back and study the formula of internal energy. The internal energy is proportional to change in temperature. If the internal energy did not change because of first law of thermodynamics, then the temperature cannot change, right? So delta T is equal to 0 in free expansion. What is the name of the process we are studying? It's called free expansion. What happens in a free expansion? The gas moves from the zone of pressure to a vacuum and faces no pressure, and hence no work is done. It expands freely. There is no work. There is no resistance. It expands freely. It is called as free expansion. Look at the question number 1. Question number C. What is the change in temperature of the gas? 0. The temperature of the gas remains unchanged in the case of uh, free expansion. All right, I hope these two are clear to you. Let's go to the part number 1. What is the final pressure of the gas in A and B? Let's talk about it. I'm referring to part A of this numerical. I know we're doing it a bit haphazardly, but physics is logic. We will go with the flow of the logic, not with the flow of the questions. Part A, P1 V1, right, is equal to P2 V2 because it's an iso. There is no change in the temperature of the gas. So it actually is an isothermal situation. The initial and final states. The initial temperature is same as the final temperature. There is absolutely no change in the temperature of the gas. So P1 into V is equal to P2. The volume of the gas doubles. It occupies both the cylinders. It's the cylinder number A and the cylinder number B. The total volume now is right this much, V and V. So there is a stopcock here, right, which is this. So the volume is V, the total volume is 2V. So the pressure now is equal to half the previous pressure. So what happens to the pressure? The pressure reduces to half because the volume doubled. The pressure reduces to 50% because the volume doubled. Question number first also answered. This was a fairly straightforward scenario, right? You know the equation. You know you're from 10th standard, 9th standard, Charles' law, Boyle's law. The number of moles have not changed. Same gas. Only it now has double the space available to it. It has double the space available. It has this V as well as this V available. So there is a change in pressure. The pressure, if I write the table, the initial and the final. Initial temperature is T, final temperature is T. Initial pressure is P, final pressure is P by 2. Initial volume is V, the final volume is 2V. In a free expansion, you can apply these equations. These equations get applied in any situation. Do not get tempted to apply the adiabatic equations of PV gamma is equal to constant. Do not do this, right? It is free expansion is adiabatic. Free expansion is an adiabatic process, right? But in an adiabatic process, Remember, there is a work done and it appears as a way of change in internal energy. In our case, there is no work done. The work done is zero. The Q is also zero. The work done is zero. The delta U is equal to zero. Is this true for an adiabatic condition? Never. In an adiabatic condition, work is done to change the internal energy and Q is equal to zero. So this is your free expansion. This is your condition number 1, 2, and 3 for a true adiabatic process. Do not apply this. Apply this for a free expansion. I hope this made sense to you. Let's go back. Let's talk about the exam question number 4. Do the intermediate states before settling to the lie on the PVT surface? Very tricky question. What does it mean? What does it mean? Let me explain you the D. D is tricky. Don't worry about the PVT, etc., etc. Do not worry about it. Now let me redraw the diagram. Okay, let me redraw the diagram with the stopcock opened and the gas moving into the second chamber of equal volume. Okay, so this was the pressure here. Now the gas is moving here. Now the gas is moving here. After, this is situation number 2 after the stopcock is opened. Now let me draw the final state. Okay, the final state is something like this. When the two cylinders again attain an equilibrium condition. Okay, let me just remove this line. So draw and let me remove this line, right? So this is not something we want. We don't want this. So I will just remove this. This is gone, right? So these are the two cylinders. Now in this particular scenario, what is happening? It is very, very interesting to understand. Let me use a different color. So this is your gas. Now this is the final equilibrium. Okay, the everything has settled. The pressure has gone down by half. The pressure all over is P by 2. We saw that, right? The volume is double V, and the pressure of the gas is P by 2. But in the situation, this is the final state. This is the situation of equilibrium. Nothing is changing now. The transit state, which is mentioned in the question, read the question very carefully. Let me take you back to the question. See this. It says the intermediate state. Transit state means intermediate. If you're moving from point A to B, all the positions between A and B will be called as intermediate positions. The gas is gradually entering. When the gas is entering, it's, and this, the final equilibrium has not been attained. This state is called as an intermediate state. Intermediate state. An intermediate state is not a state of equilibrium. No equilibrium is here. No equilibrium is here. The question is, can we, draw a graph? Can we write anything about this particular state where the gas is entering and freely expanding into this? Can we do that? It is not possible. You can only do graphs and equations for final positions when equilibrium has been attained. When the gas is in the process of free expansion, the free expansion is happening. You cannot write or draw any graph at all. You cannot do that. Let's go back to the question. It says, is the before settling to the final equilibrium. The settling phase is this. This is the settling equilibrium, right? Let me write it as settling equilibrium. Settling equilibrium. Finally, the pressure reduces to half. The volume is double. This is the, and of course, the state number 1, when they were, separated by a stopcock. So there is a stopcock here, right? It stops. Even this state is a state of equilibrium. First state is equilibrium, but the gas here is only here, right? This is vacuum. In the second state, free expansion is happening. the third final equilibrium is attained. This is the way it works. So the answer to this problem is it is not possible for us to draw the graph, okay, the lie on its PVT surface. No. Answer is no. Intermediate states cannot lie on any surface. It is not possible for intermediate states to be on any surface because they have absolutely no equations associated with it. So if you have a PV situations, PV equations, the only way you can draw the PVT, right, for a particular temperature is at equilibrium. You can do this here, you can do this here for a particular temperature, but you cannot apply PVT surfaces for intermediate states because there is no way you can plot, you cannot plot a PV graph for expanding gas. A PV graph can only be plotted for initial and final positions. The intermediate positions cannot be drawn. This is what it means. So the answer is no. The intermediate state where the gas is expanding cannot be plotted on the PVT surface. PVT surface, right? I will talk about PVT surface later. You must understand what are PVT surfaces, but I hope for the time being you're able to appreciate that we cannot have any mathematical explanation or equation or graph for free expansion stage. We can only do that for equilibrium. The equilibrium number one is equilibrium when the stopcock is still there. When you open the stopcock, the gas is expanding. Nothing is allowed, no equations, no graph. After everything settles, which is the state number three, the pressure reduces to half, the volume is double, you are allowed to plot. This is a scenario where you cannot plot or make equations, and therefore you cannot have the state on the PVT surface. We will talk about PVT surface in detail. I hope you understood this. 2500 numericals on this channel, the only channel which is giving you explanation. The logic will stay with you forever. A lot of concepts are getting covered in the questions. Do not miss any of this. Subscribe to this channel and ensure that you make a good career, you prosper. Our aim is to impact 1 million students in the country. We want to change the way physics is taught. We do not want physics to become a joke or gimmickry. It should be real good physics so that you actually build careers. You're not here for entertainment. You're here to build life. Thank you very much. Have a good day.